Hi, I'm Aliaksei, and today I'm going to talk about our paper called Active Sampling for Pairwise Comparisons via Approximate Message Passing and Information Gain Maximization. Consider, for example, chess tournaments where we want to infer the scale or the ranking of the players in as few games as possible. Similar problems occur in hospitality and restaurant services. Pairwise comparisons are commonly used for scale inference. In the next slides, I will be referring to the compared entities in pairwise comparisons as conditions. That would be either players in a game or restaurants in a questionnaire. One of the major drawbacks of pairwise comparisons is the large number of possible pairings. And the natural question is, how can we minimize the number of comparisons while inferring as much information as possible about the relative position of the conditions in the scale? Generally, two types of methods are distinguished. Sorting-based, using simple heuristic, that simple inequality or in scale conditions should be compared, and information gain-based. Those use the pairwise comparisons that would be minimizing the uncertainty in the scale the most. And our method falls into that category. Information gain-based methods follow a similar pipeline. We start with the data collected so far, that would be pairwise comparisons. We would then infer the scale. Here, most of the methods approximate the scale so that they can maximize the computational efficiency of the algorithm. Unlike them, we use full posterior update and hence obtain a very accurate scale. Once the scale is available, we can select the next comparison. Here, most methods do not improve the speed, unlike us. Once the next comparison is available, we can run the experiment. That would be either a chess game or again a questionnaire for the restaurants. Once we have the outcome, we can update the data. For scale inference, we use true scale algorithm, and we are interested in the score variable given the outcome of the game or pairwise comparison. We use sum product algorithm with expectation propagation via moment matching. The algorithm is iterative with the complexity of n plus t to infer the scale, where n is the number of conditions and t is the number of comparisons collected so far, and k is the number of iterations. Typically 10 to 15 iterations are used. Once we have the scale, we can now figure out what would be the best next comparison to perform. We start with the data collected so far. Here, in every row and column, are entities that signify the number of times the condition in the corresponding row was selected over the condition in the corresponding column. Consider, for example, conditions 2 and 3. 3 was selected over 2 one time and 2 over 3 three times. We then simulate all possible comparison outcomes for every possible pairing. At the top, we simulate the outcome for 2 selected over 3, and at the bottom of 3 selected over 2. We then infer the scale and compare the scales with their original data and assumed possible outcomes with the KL divergence. And then we calculate the expected information gain with respect to the probability of the comparison outcome. One of the drawbacks of such an approach is that we would need a large number of comparison outcomes to consider. And we consider two strategies to improve the speed. One of that is selective expected information gain evaluations, where we evaluate expected information gain only for a subset of possible outcomes, and batch mode, based on the minimum spanning tree. In the selected expected information gain evaluations, with the lower probability, we would be calculating expected information gain for the conditions that are far apart in the scale, and for conditions close in the scale, we would be calculating expected information gain with a higher probability. For more details, please refer to the paper. In the batch mode, we treat all conditions as vertices. Edges between those vertices are possible comparisons. We then weight the edges with the inverse of the expected information gain. So where the gain is large, the weight is small. After that, we select comparisons, forming the minimum spanning tree. We run the Monte Carlo simulation to figure out what methods perform the best. Here, on the y-axis, we plot RMSE, root mean squared error, and on the x-axis, we show the number of comparisons performed so far. Here we can see three distinct classes of methods. Sorting-based methods that perform the worst, then methods based on the approximate inference of the scale, and then ASAP, with the full posterior update performing the best. How does this accuracy convert in the experimental time? So here we want to achieve 0.15 RMSE in the scale, and assuming that it takes 5 seconds to find the outcome of the pairwise comparisons, how much time would we need to spend in the lab running the experiments? For 20 conditions, with ASAP we would require slightly less than 50 minutes to obtain the scale with 0.15 accuracy and RMSE. and that would require 3 times more than second best performing method. For 200 conditions, we would need slightly less than 10 hours in the lab with ASAP. Our method achieves state-of-the-art results due to the full posterior update in the computation of the score distribution. Other methods rely on partial approximate update. We make the method computationally feasible by evaluating expected information gain only for a subset of conditions, reducing the computational cost by up to 80%. We also select a batch of conditions, making the algorithm computationally feasible for crowdsourcing experiments. Please feel free to check out the code and the paper. There are much more results in the document. Thank you very much, and I'm looking forward to your questions.